Hello everyone, welcome to TLE Eliminators. This is Vibhaas, and today we'll be discussing the Leetcode post contest discussion for the biweekly contest 164. Before we start, how was the contest, guys? Um, B was a bit hard, I could say. Even I took some time on it. A and C were easy, yeah. A and C were easy. B was quite tricky. All right. D was DP, yes. D was not exactly DP. It was like DFS kind of thing. Um, yeah, we'll get right into the problems. Before we start, I'd like, if you haven't seen them before, we at TLE Eliminators have courses, self-paced courses, which are divided into 4 different levels. You can go to tlelimiters.com/courses to check them out. These can take you through all different levels of competitive programming, starting at the very beginner level by teaching you C++, math, space and time complexity, all the way to level 4, which teaches you topics like dynamic programming, graphs, DSU, segment trees, etc. Right? So these courses are for someone who wants an ordered and structured approach to their competitive programming, because although there are a lot of free resources available, sometimes doing free resources you'll never be sure whether you're going in like the correct direction or not, right? So if you ever have that doubt or you feel like you're stuck and you can't make progress, then do check out the Eliminator self-paced courses. Each course has more than 40 hours of recorded lectures, more than 100 plus curated practice problems, hints and video solutions for all the problems, as well as doubt support, which is available almost 24/7, right? As well as a leaderboard, so you're motivated to keep solving. So yeah, do check out T Eliminators courses. They're at super affordable prices, right? Each course is catering to a certain level, and you can choose which level and which topics you want to study, and you can join that course, right? All right, let's get started. Um, yeah, long time no see, guys. Okay, we'll be going to start with problem A as usual. I won't spend much time since it's pretty simple. Given an integer n, find the digit that occurs least frequently in its decimal representation. If multiple digits have the same frequency, choose the smallest digit. Return the chosen digit as an integer. Okay. So very straightforward question. They literally tell you what they need. You must just implement. So if you're good with any programming language, no matter which one it is, you will be able to solve this. So basically they have the number one. They have the n equals this number like 1553322, and the number one has the digit one has the least frequency in all of them, right? 5 has frequency 2, 3 has frequency 2, 2 has frequency 2, so 1 has a frequency of 1, so that's why the answer is 1 over here. Similarly, in this case, all the digits have frequency of 2 except for 5, 2 and 7, which have a frequency of 1. In that the smallest one is 2, that's why we're printing the answer 2, right? So I think this one is pretty simple, nothing much to think about, so I'll get right into the code, right? So problem A, and it's basically the way I solved it was for C++, right? Yeah, I'll tell you the implementation level details. So the way I solved was for C++, and I converted n to a string. So I made a string to string of n, right? Then what I did was I stored the characters of this string in a map. Obviously you can do it with just arrays, and that will be faster, but in a contest I just want it to be simple, so that's why obviously the constraints are pretty low, so there's no problem, right? The number of digits will be at most 15 or something, so it can't be more than that. So n is very small, right? Effectively the number of digits. So yeah, I stored these in a map. Store characters of s in a map, um, in map, right? And in the map what I did was basically map of the character plus plus, right? So basically this is what I did. Yeah, and then I found in the map, like I iterated through the map, um, right? So auto in map, and then I found the character with the smallest value of y, and I print, and basically I returned that value. And obviously let me just show you the code directly, right? So basically you have your map of x and y for each character, so each character and the number of occurrences. Now if the current character, if your current character has more number of occurrences than this particular character, then you simply switch c equals x. Similarly, if the number of occurrences is equal and x is smaller than c, then you will set c equals x, right? So in the end, after this loop, c will have your answer. C will have the character with the minimum frequency, and among those it will be the minimum one. So we simply convert it back to an integer and return it. So that's all is the logic for this question. Obviously you can implement it in many different ways in many different languages, right? Okay, so I think that's all for problem A. The time complexity is of course big O of log of the number. Why log of the number? Because it's big O of number of digits, right? So find min frequency, min digit of that frequency and return it, right? And the time complexity for this is obviously big O of number of digits, which will be big O of log to the base 10 of n, right? So which is big O of log n, right? So this is the time complexity for the given problem. Okay, let's move on to the next problem, problem B. And yeah, problem B took me quite a lot of time, and I think it was pretty hard compared to the usual problem B we see on Leetcode. I think it was harder than C as well, but that depends on you. The idea was basically thinking greedy and nothing much more than that, right? Any doubts on A? Any doubts with problem A, guys? Should we go on? Yeah, okay. So now let's start problem B. Problem B is 2-letter card game. You're given a deck of cards represented by a string array cards, right? So there is an array called cards which has a string of cards. Each card has 2 lowercase letters. Okay, so each card is 2 lowercase letters, like A B, C A C D, something like that. So each card has 2 lowercase letters. You're playing a game. You start with 0 points. On each turn, yeah, so you're given letter X. Okay, so on each turn, you must find 2 compatible cards from the deck that both contain the letter X in any position. Remove this pair of cards and earn 1 point. The game ends when you can no longer find a pair of compatible cards. Return the maximum number of points you can gain with optimal play, and it's defined that 2 cards are compatible if the strings differ in exactly 1 position. Okay, so let's just summarize what all it said. So it said basically we need to find the number of pairs, of cards we can form such that 1, both cards contain the letter X, right? At least once both cards contain X, whatever that X is as an input, right? It can be any letter. And second, they should be compatible, so they differ at exactly 1 point. They differ at exactly 1 point. So if they don't differ at all, then also it's not allowed. Okay, so they must differ at exactly 1 point. So these are the given conditions, and we need to find the maximum number of such pair of cards we can form in the given cards. All right, let's take an example. Let's just see the first example. So we have AA, and we have AB, and we have BA, and we have AC, right? And our given X is equal to A. All right, so which cards contain A? Right now in the set, all the cards contain A. Obviously, if the card did not contain A, then there's no point. We might just not even consider it. right? Okay, so now this card, let's say we paired with this card because they differ at exactly 1 point, right? And they both contain A. Similarly, we can pair this card and this card as they also differ at exactly 1 point and they both contain A, right? That's why the answer for this case is 2. Okay, so I hope you have understood the question exactly. We have to find the number of pairs we can form so that both cards contain some given input letter X and that they differ at exactly 1 point. Okay, so the question I hope is clear, right? Okay. Yeah, I think question number 3 was more doable than this one. Anyways, although question number 2 does not take any specific background knowledge, right? Question number 3 requires you to know DP or like grid counting. Question number 2 is pure logic, pure math type of question. Okay. Now, how do we find these cards? Okay, so we have to make a bunch of observations which we will logically break down the problem. Okay, so the first observation which we will make is, let me just put it right here. The first observation we're gonna make is right, first observation, and that's basically going to be the fact that since we know that both cards contain X, let us think about what are the possible pairs we can have, right? So one way we can have a pair, a valid pair, is if we have X, right? Let this be X, so this capital X and some value, let's call that A, with XB. Okay, so basically A and B are different, they can be any values. I'm just writing them as A and B. Okay, and so this is one valid way we can pair two cards up. Basically, for example, here it will be the same way we paired AB and AC, right? We paired AB and AC. So AA is same, B and C are different. So AA is same, right? And B and C are different. So basically that's what pairing we have done over here. X is the given value which we had, okay? Or we have paired the form AX with BX, right? Where A and B can be anything. X must be equal to the X in the input, or basically we have the values which are like XX with AX or XX with XA. Okay, so these are the 3 or 4 cases of pairing which we can do. Okay, are you following, guys? Is this understandable? I hope I didn't write it too generally. Basically what I'm saying is the kind of pairing. Let us take example X. Let me write example. Let's say X equal to P. Okay, X is equal to P. Then over here this will be like we can pair PC with PD, or we can pair PQ with PY, something like that, right? So that will be of this first form. Now the second form is going to be something like DP with SP or QP with ZP, right? So this is the second form of pairing, and the final form of pairing will be something like PP with PZ or something like that, or PP with SP, something like that, right? So basically these are the 3 types of pairing which we can do. Okay, so I hope this much is understandable. So please note this as the first observation. Okay, so basically the type of cards we care about are either of the form XA, AX or XX, right? So from this we get that let's say there are 3 type of cards. Okay, so there are 3 types of cards. Type 1 card is basically XA type. Type 2 card is going to be AX type, and type 3 card is going to be XX type. Okay, so obviously we can pair AX with AX, we can pair XA with XA, AX with AX, and XX we can pair with one of these two, right? So these are 3 types of cards, and we need to form the maximum number of pairs between them. Okay, so the first thing we'll do, first and most logical thing to do, logical thing to do, thing to do is to count how many type 1s are there, how many type 2s are there, how many type 3s are there, right? So we will count type 1 cards. So let me write as number of, count number of type 1 card, type 1 cards. Also we'll count the number of type 2 cards, right? Type 2 cards. And we also count the number of type 3 cards, right? Now number of type 3 cards, right? So I hope this much is clear. Okay, and what, let's just give them some variable names. So in my code I call them n, m, and k. So type 1 cards I'll call the count will be n, count is n. Type 2 cards the count is m, and type 3 cards the count is k. Okay, that much fine. All right, so now we have to start thinking about how to pair them up, right? We know that we can pair type 1 with itself, we can pair type 2 with itself, and we can pair type 3 with either one of those two, right? So the first thing we'll do is, first thing we're going to do is try to pair as many as possible, as many as possible in type 1 first, in type 1, then try to pair as many as possible in type 2, in type 2, then try to pair as many as possible, as many as possible from type 3 to any of these. Okay, from type 3 to, from type 3 to the previous two. Okay, and that's what we're going to do. Basically first we'll pair amongst these xa types, then we'll pair amongst ax types, then we'll try to see how many xx we can match with these. All right, so let me give you an example. Let's say I have my target x is equal to a, and my strings are going to be, let's say ab, ab, ac, ab, ad, right? So let's say these are my strings, and then after that I have ca, da, ea, fa. Okay, then I also have aa. Let's say I have one aa. Okay, so then which ones are type 1s, which one are type 2, which one are type 3? We can say that these are type 1s, right? Type 1, these are type 2, and these are type 3, right? So we have classified them to different types. So first we'll try to form pairs amongst them. Now obviously we can't pair these two because they're the exact same string, and for strings to be compatible they must be differing at one point, right? So we cannot pair like this. So one way we'll pair it is we'll find ab, pair it with ac. Okay, then we'll take this ab, let's pair it with the ad. Now this one ab is remaining, let's leave it as is. Okay, so we formed two pairs from type 1. Now what about type 2? In type 2 all of them are different, so we can pair ca with cd, ea with fa, and we form two pairs again. Now we have a type 3 left, and if you remember, type 3 can be paired with type 1 or type 2, and this card is remaining, so we'll pair these two. Okay, so we pair these two and we got one more pair. So the total answer is 2 plus 2 plus 1 equals 5 for this test case. Okay, so basically we need to pair internally between type 1s, pair internally between type 2s, and then pair with type 3s. And we're going to assume that this strategy may or may not work, but first we'll try this. Okay, this strategy is not complete yet, but we're going to try this and we're going to see what happens. Okay, now we have a sub problem. We get a sub problem. Let's say we take type 1. Okay, type 1 and type 2 are similar, so let's say we take type 1 and we only have the type 1 cards, and we need to find out how many max pairs can we make. Okay, how many maximum pairs we can make. Fine. Only of type 1 cards we can make. So here the problem mainly is that some cards are equal, so they cannot be paired together, and different card, they can only be paired with different cards, right? So for example, if we have AB, 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 and A is equal to X, right? And then we have, let's say, AC, AC, and we have AE, something like this, right? So we know that we cannot pair B and B. Similarly, we cannot pair C and C, right? We must only pair different ones, right? So the question is, how many pairs we can make if we can pair only different elements? If we can pair only different elements. So now, how many of you can solve this? Like, try and pause the video if you want and try to solve it, okay? Because yeah, so try and solve this sub problem, because this actually is a very standard greedy problem to try to pair. If we can pair objects, but we can only pair different type of objects, and we have some counts of the objects, how can we pair them, right? So for example, the counts over here are 3, 2, and the ways we can pair are basically we can pair two of these with two of these, one of these with one of these, okay? So let us write, let's say, a different arrangement. Let's say we had 1, 4, 2, 3, 5, 2, 1, 6, or maybe 2, 1, 3 again, right? Now if the array was something like this, okay, then how would we know what to pair? So for example, this is AB, and then this is, there are 4 ACs, right? There are 4 ACs, and here let's say there are 2 ADs, right? And so on. Now we need to figure out what is the maximum number of pairs formed. So the solution to this problem is a known solution, and basically, first of all, think we are pairing them up, right? So since we are pairing them up, the maximum answer will be less than or equal to n by 2, right? The answer will be less than or equal to n by 2. And also, there is another case. What if the maximum one was very much in number? Okay, what if the maximum one was very much in number? So let me show you a case like that. Let's say we have 1, 2, 10, and 2 again. Okay, so basically we have AB. Let's say we have AC, AC. Then we have AE, AE. And the ADs, we have 10 of them. Okay, so we have 10 ADs, right? We have 10 ADs. We have, let's say, 10 ADs. And let me just write them quickly. Yeah, we have 10 ADs and we have these other numbers. So now how do we pair in such a case? Well, we can simply pair the AB with one AD, and we can pair AC with one AD, similarly AC with another AD, and so on. But then these 5 will be unpairable, right? These 5 will be unpairable. They will be left remaining. So basically, if the maximum value out of these frequencies, if the maximum value in this frequency array is larger than the sum of the others, then that much is going to be remaining. Okay, so let this array be called A, and let us discuss max A. So now if max A is greater than n by 2, right? If max A is greater than, if max A is greater than the remaining elements, so if max A is greater than n minus max A, then what is going to happen is the total number of pairs which can be formed will simply be n minus max A. Okay, otherwise the total number of pairs which can be formed will be equal to n by 2. Okay, and you can show that if the max element is less than if max A is less than n minus max A, then you can always pair it, right? Because you can always choose the largest frequency and you can pair something else, and you can repeat the process. So this is a known greedy problem, and the solution to this is basically, if the maximum frequency element is greater than n minus max A, then the number of pairs can be formed is n minus max A. Otherwise, the number of pairs which can be formed is n by 2. Okay, so yeah, I can prove that we can get n by 2 and not less than that. For example, let's say we had the case again like 5 2 3 4 1 3. Okay, in this max a is 5, max a is 5, and the total n is how much? 5 plus 2 plus 3 plus 4 plus 1 plus 3, right? So how much is that? That's 10 14 15 18, right? So total n is 18. So let's check, is 5 greater than 18 minus 5? And how much is 18 minus 5? 18 minus 5 is simply 13. Well, we can see that 5 is not greater than 13. That must mean that the number of pairs formed is 18 by 2, right? Or 9 pairs we can form, right? And I'll show you that we can form 9 pairs. And the reason is we always choose the max element and we start pairing it up with the others. Okay, so for example, the max element is here, 5 are there, so we'll pair 2 here, 3 here. So now this is 0, this is 0, this is 0. Now again in the remaining one we choose the max element, which is 4, and pair them up, and then this will be 0, this will be 0, this will be 0. So we have formed n by 2 pairs, right? So in the case that the max element is small enough, we can form n by 2 pairs. If the max element is bigger than the sum of the remaining, then we cannot form n by 2 pairs, right? I'm not sure what the name of this is, but then the it's a very standard thing. Like I've seen it like multiple times before, but I don't think it even has a name. It just, if you practice enough greedy problems, especially the basic, like if you take a greedy set of maybe 20-50 questions, you will definitely see this idea a few times. I'm not sure what this idea is called though. Sorry about that, Abhay. Okay, let me just see if there are any doubts, because this is a maybe something not everyone will know, right? Okay, look, we'll move on to third problem soon, right? Don't worry about it. Yeah, okay, so the answer is not complete yet. We need to continue working on it. Let's see, there are some doubts, I think. Cosmic boy, please just write your whole test case. I don't know exactly which example you're referring to. What if there was 6 in place of 4? I don't know which example you're referring to. How is the answer 1 for AB and BB? X equals B. You can simply pair AB with BB, right? So the answer will be 1. Since they both share the common value of X, which is B, and they have differing at one point, one is A, one is B, that's why the answer is 1. So I don't know why global marketing and services. Anyways, okay, so then this is the logic for setting max A, and actually we can write this logic in a simple one line logic. So this is a known problem, and you can see that the logic can be written like this. The number of pairs formed will be equal to the minimum of n by 2 and n minus max A. Okay, so in these two cases, the number of pairs which are being formed, if you take simply minimum of those two cases, that is the number of pairs you can form, right? And the reason is, if n by 2 is smaller than n minus max A, that means that n max A was small and we can make n by 2 pairs. If n minus max A was smaller, that means that the sum of the remaining elements is smaller than n by 2. So that's why we can only form n minus max A pairs, right? So basically the logic, the same logic can be written in one line like this. Okay, one liner. Okay, now how many unpaired does this leave? How many are the unpaired? The number which are left unpaired in this process, left unpaired, we have to keep them in track. So the number which are left unpaired equals to n times to n minus 2 times the paired ones, right? So these are the ones left unpaired. So these are the pairs formed, and these are the ones which are left unpaired. Okay, I hope you're following me. Okay, now for the other case as well, type 2, for the case of type 2, the logic, exact same logic will work, right? Type 2 cases, basically instead of having XA, we have AX types, right? So that's what type 2 is. So AX type case, AX case, exact same logic will work, and we can tell you that the answer of will be, the number of pairs will be pairs, let's call it pairs 2, and the number of pairs formed using this type 2 will be the minimum of m by 2, since we said the number of type 2 is m, so it will be m by 2, and let's say m minus max b. Okay, so max b is the frequency array of the type 2 values. Okay, so max b, and max b is the maximum one with the maximum frequency, right? And again, left unpaired, how many are left unpaired? Again it will be m minus 2 times pairs 2. Okay, so keep this in mind. This is part 1, solution to part 1 is solution to type 2. Okay, now what about type 3, right? What about type 3? So there are two things which type 3 can do. Okay, first is the ones which are left unpaired from the previous process, it can pair with those. Okay, so pair with the ones left unpaired. Okay, so let's say there are k of these, they are k of type 3, right? So basically our answer, the number of pairs we have formed, the answer increases by minimum of k and the ones left unpaired, right? So if there are many left unpaired and k is smaller, then only k we can make more pairs. Otherwise, if unpaired is smaller and k is large, then we can pair with the ones, right? So answer increases by this much. But there is one final case. Okay, so right now our answer is equal to pair 1, which is made by type 1, pair 2, which is made by pairing type 2, plus the minimum of k and the unpaired ones. Okay, the minimum of k and the unpaired ones. However, there is still some part of the question left. So if you just stop at this and submit, like in my first solution I just submitted this, but this is a wrong answer and there is still one observation left. Okay, so the remaining unpaired values are the remaining values of type 3, the remaining values which are like AA form, right? The remaining AA form or XX form, those can still be paired with the original ones, and I'll show you how. Okay, so basically we have k minus unpaired of them left, right? If k is greater than unpaired, if k greater than unpaired, then k minus unpaired type 3 is left. Okay, type 3 cards are left over. Can we use them to increase our answer? Okay, can we use them to increase our answer? Okay, so that's what we need to consider now. And yeah, I know this problem is getting a bit complicated. That is because it was a complicated problem, so don't worry too much about it, right? If you're getting confused at any point, you can always pause it and rewatch, go through it carefully, because there are many steps to consider for this problem. Okay, so now k minus unpaired type 3 cards are left. So for example, we have type 3 cards like AA, 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 right? And let's say 3 of these are left. Now in the original pairing, let's say we had a pair of AB and we had a pair of AC, right? So these are type 2 pairs, and let's say these two were paired together, and they form up one pair. Okay, they form one pair. Now the interesting thing is, if we break this pair, then the total number of pairs becomes -1. But then this AB can be paired with this AA. Also, this AC can be paired with this AA. Okay, so this AB can be paired with this AA. This AC can be paired with this AA, and that means that two new pairs were formed. So one pair was broken, and two new pairs were formed. Right. So basically that means +1. Right. So basically overall +1 pair has been formed. Right. So basically we broke one old pair, break a pair of type 1 or type 2, form two new pair of type 3, right? Using type 3, basically AA and AB and AA and AC, and we form this new pair, right? So the remaining unpaired, the remaining k minus unpaired type 3 cards, we can do this with the type 1 and type 2 pairs, right? So we can do this as many times as we want with the type 1 and type 2 pairs, as long as we don't run out of them, right? So by using two cards from here, we're able to increase by one pair, right? So basically we can do this for k minus unpaired divided by 2. Okay, k minus unpaired divided by 2, these many cards we have remaining, and those we can do this process with, right? And obviously the number of type 1 and type 2 cards also limited, so that's why um, we can do this a total of pair 1 plus pair 2 times, right? So minimum of these two. Basically what I'm trying to say is, let's say we have type 1 pairs, and let me just write some pairs for you. Let's say we have BA CA, which is one pair, okay, and then we have CA DA, which is one pair. Okay, so these are two pairs of type 1. Now we have some type 2 pairs as well, type 2 pairs, okay, and let's say those are AB AC, we have AC AD, and we have AC left over. Okay, so then these are the type 2 pairs formed, right? And now let's say type 3 we have left, type 3 we have left 3 AAs. Okay, we have 3 AAs left over, right? So the first thing we do is obviously pair with the unpaired. So this one is unpaired, so we can pair these two, right? So now we have a total of 1 2 3 4 5 pairs. Okay, now these two are remaining. Two of these AAs are remaining, right? These can also be paired, and what we can do is we can break a pair from here. We can break this pair, and we can pair this with this and this with this, right? Or something like that. We can pair this with this with this. So let's do that. We break this pair. So now the number of pairs becomes 4. Then when we pair this with this with this, now the total number of pairs becomes basically this will become the fourth pair, fifth pair, sixth pair, right? And so total number of pairs becomes 6, and that's what my idea is basically. So it will be limited by k minus unpaired by 2, which is the number of k values over here, right? So let's call this k dash. It's the number of k dash values, and also obviously this is total pair 1 and this is total pair 2, and that's how many we can break, right? That we can only break pairs which already existed, so that's why this. So min of these two we can increase our answer with, right? So I hope you followed. Let's see. On each turn, you must find two compatible cards from the deck which both contain the letter X in any position. I do not know what you mean exactly. This note is very clear to me. Okay. How did I build the intuition of maxi greater than n minus maxi? It's a very standard greedy problem, first of all. So while solving this question in this contest, I already knew it from before. And the second thing is, yeah, if you did not know this before, it would take some time to build the intuition. But basically the idea is that you have to sit down and try pair, right? If you try some examples and try pairing them up, first thing though you will notice is this case should come pretty simple, but to prove this case might take some time, right? Because obviously if one is much bigger than the others, then you can never pair them up. So that's where the intuition came from. This is for Steve Harrington. Okay, did anyone get this on the first try? I don't think so. This took me three tries to get this. Why divided by 2 in k minus unpaired? Okay, Prince Raj, that is very simple. That's because we need two of these cards, right? We need two of these cards to break a single pair, right? We need two of these cards to break a single pair over here. And the reason is because we are forming two new pairs, right? So we need two of these to form a single pair over here. That means we need pairs of the cards of type 3. That's why we're doing divided by 2. Okay, Prince Raj? That's why we have k minus unpaired divided by 2. This has become a lot now. Yeah, it is pretty. I mean, the code is short itself. The code is pretty short, but the logic is pretty deep. Yes. Yeah. What if there aren't any type 1 and type 2 pairs? That's the thing, right? If you have enough excess type 3, then by breaking type 1 and type 2 pairs, eventually you can get to the case where all are type 3 pairs as well. So this logic handles all of that cases. Yeah, the edge case is pretty tricky. Yeah. Yeah, Steve Harrington, if you're getting stuck with the min n by 2 n minus max a, you can just go back and see the logic at that point. I did give an example or two for why that's true. Can I explain the edge case again? See, the edge case is basically just the fact that you can break a type 1 or type 2 pair and form two pairs of type 3. So we're going to try to break as much as possible, right? Because we're getting one extra pair each time. And the number of pairs extra we can form will be this. This will be the number of pair 1 plus pair 2 which we can break, and this is the number of k minus unpaired which are there, right? Each time to form two new pairs, we're taking two of these k minus unpaired. That's why it's being divided by 2. Okay, let's have a quick look at the code. Maybe that will clear it up. Maybe the code will make some of the logic more clear. So this is the code for the problem. N, M, and K are the count for type 1 and type 2, type 3, right? So count of type 1, type 2, and type 3. Okay, so that is N, M, and K. Map of A and B is going to be used to measure the frequency of type 1 and type 2. Okay, so used to measure frequencies of type 1 and type 2 cards. Okay, because we need to find the max one, right? We need to find the one with the max frequency. That's why we're measuring their frequencies using the map. Okay, now for each card, if the card is equal to XX type, that means it's type 3. So we do K++. Otherwise, if the 0th value is X, then we can increase the corresponding value in the map and we can do N++, right? So this means type 1 and this one means type 2, right? So we're just increasing N, M, and K and we're adding them to the maps. Now, what is A max and B max? That is going to be the maximum frequency of type 1 and type 2, right? So A max is the max frequency of a card of type 1. Similarly, B max is the max frequency of a card in type 2, right? And why are we finding the max frequency? Because then we can use the logic of n by 2 or n minus A max, the min of these two, right? We need to find this value for finding how many pairs we can make. Okay, so now pair 1 will be the type 1 pairs. Pair 1 will be the type 1 pairs. Pair 2 is going to be the type 2 pairs, right? Type 2 pairs. And unpaired is the one which is being left unpaired with the initial process, right? Unpaired are just unpaired. The name is self evident. Okay, so pair 1 will be equal to this, as I explained. The unpaired increases by the ones which have not been paired. Similarly, pair 2 will be equal to this logic which I had explained earlier, and the unpaired will be equal to the remaining values. Okay, so now we have our answer. We have this preliminary answer, right? Which will be simply pair 1 pairs plus pair 2 pairs with a type 2 plus the remaining ones can be paired with type 3, right? This will be the preliminary answer. Now this is the edge case. And the edge case is basically we can take type 3s. We can take type 3s and we can start breaking type 1 and type 2 to get one extra, right? We can take type 3 and start breaking these and then pair them up. So that's what we're going to do here. So we'll increase the answer by the amount of breakages we can do. And basically the amount of breakages we can do is first limited by the number of pairs initially and also limited by the remaining k values, right? So we need k by 2 or k minus unpaired by 2. So that's what the answer increases by. And then finally, once we're done all this, we can return the answer. So yeah, it's a pretty complicated greedy with several cases. But then this n by 2 n minus A max Easy standard greedy idea, used over here. Okay, so for this I'm not exactly sure, I can't right now tell you a problem where this was used before. But see, you're seeing it for the first time right now. If you're seeing it for the first time right now, then definitely make a note of this. Make a note of the sub problem, right? That if you have a bunch of values and you need to pair them up, each thing can only be paired with a different value, then the answer will simply be n by 2 versus n minus a max, right? So may definitely make a note of this, right? If the maximum one dominates, then the number of pairs will simply the one with the maximum one, otherwise it will be n by 2. So this logic, please keep that in mind. If you want to rewind the video, I'd explained it step by step also why this is true, with a proof as well, right? Okay, what is the time complexity of this? Because I'm using maps, the time complexity gets a bit of a log factor. But otherwise, if you remove maps also, you can just use arrays. In that case, the time complexity will simply be big O of n, where n is the number of cards, right? So depending on your implementation, the time complexity of this will be big O of n or n log n, depending on how you implement. Okay, big O of n or big O of n log n. Because I used maps for convenience, it's n log n. Sai Siddharth, you cannot simply sort the type 1 and type 2 cards and pair first and last card if they're different, because the thing is, you might, what do you say, like, you might pair them in an unoptimal fashion, right? The optimal fashion to pair such that you get an n by 2 of answer, such that you get the n by 2 answer, is that you always choose the max one, the card with the maximum frequency, and you pair it with some other card, right? So each time you pair the card with maximum frequency with some other card, then you can ensure the optimal answer of n by 2, right? Or n minus a max. If you just simply sort and pair in any order, you might not reach that optimal answer. So this answer is for Sai Siddharth. Okay, so I think we spent enough time on B now. We'll be moving on to C, right? If you have any doubts, please just rewatch the video. That helps a lot. Take notes, right? Okay. So from problem C and to some extent problem D, they are more standard, I think. So I'm like less complicated or tricky. At least problem C was very simple for me. Okay, problem C. So I'll just take a break of a minute and come back. I'll be right back. I need to drink some water and I'll be right back. All right, and then we'll start problem C. All right, everyone, I'm back. Um, let us go to problem C. It's not problem C is not that complex actually. So for problem C, there will be some prerequisite, and one is simply grid DP. I can explain grid DP to you right now itself, but if you know it from before, it will be easier to understand. Okay, grid, path counting, DP, which is a very standard DP to do. Okay, so this is like a prerequisite for this. Again, let us see the expected time complexity. For this question, we need to keep in mind the time complexity of the grid. So here is going to be an m less than 500, right? So before even reading the question, we can just tell you that big O of n cube solutions max, right? Max. Okay. So the question goes, given an m into n binary grid where grid of ij equals 0 means it's an empty cell, grid of ij equals 1 means it's a mirror. A robot will start at 0 comma 0 and he wants to reach m minus n comma n minus 1. It can only move right or down. If the robot attempts to move into a mirror cell, it will be reflected before entering that cell. Okay, it will be reflected before entering that cell. If it tries to move right into a mirror, it's turned down and moved into a cell directly below. If it tries to move down into a mirror, it is turned right and move into the cell directly to the right of the mirror. If this reflection would cause the robot to move outside the grid boundary, the path will be considered invalid and should not be counted. Return the number of unique valid paths from 0 to 0 to m minus 1 n minus 1. Okay, so basically we need to count the total unique paths to the destination, and we can move right or down. But if we are in a mirror case, if we are in a mirror cell, then our option will be forced, and basically we can only move the specific way. Okay, so that's basically the question. Again, m and n goes up to 10 power, m and n goes up to 500, so we can use n cube solutions as well. Okay, so let's just write all our observations down. Okay, so our observations are basically let me just write it down. So basic question observations. So the first thing is, can move right or down, can move right or down in a normal cell. Okay, in a normal cell, fine. In a mirror cell, in a mirror cell, if we entered it from the right, if we entered from R, then we can only move down. If we entered from down, then we can only move right. If we entered from down, we can only move right. Okay, does that make sense? Please start from recursive code. To be honest, I am very not used to recursive code, so I will try to give you a general idea, but I don't think I'll be starting with memoized or recursive code. I'll be explaining, like, if you know grid dp, then it should be fine, right? You will know the recurrence. Yeah, so we'll be doing it that way. Anyways, yeah, so what are the observations on this? So the first thing you need to know is, I'll explain grid counting dp, right? I'll explain some grid counting dp and grid paths counting. Okay, so let's say I have a grid and it's something like this. Okay, so the way grid counting dp works is, let's say we can only move right or down. Moves, these are our moves. At any position we can move right or down. Target is this bottom right corner, target is this. So let me just mark our target with green. So this is the target and this is the start position. Okay, start position is this one. Okay, and we can only move right or we can move down. So we can move right side, we can move down side, and we have to count the number of ways to reach it. All right, so let's say we have, okay, so what we're going to do is, basically we're going to consider dp states. Okay, we're going to consider dp states. Consider dp states which will be of the following form. Okay, so dp of ij, so I is some cell, right? I is the ith row, So let's say this is some I and this is some j. Okay, so this is some I and j. So what will be the dp state of this cell ij? And basically it will be um, number of ways to reach the target, to reach the target starting at this cell, starting at the cell ij. Okay, so the number of ways to reach the target starting at the cell ij. So let's say the number of ways were like 15 or something, then that would be the answer for dp of ij, right? So then our final answer, the final answer or our goal state will simply be dp of 0 comma 0, right? Our goal state will simply be dp of 0 comma 0, because we want the number of ways to reach the end from the start position. So our goal state will simply be dp of 0 comma 0, right? That's our target. If this is our dp state, then this will be our goal state. Okay, what is our base state? What is the state at this point? This point is dp of m minus 1 n minus 1, right? So what is our dp value over here? Well, if we are already at this position, then the number of paths will simply be 1, right? So we just need to stay at this position and the number of paths will simply be 1. So the value of dp over here is 1. Okay, so the value of dp over here is 1. So this will be our base state. Base state is so goal state means return this value, and our base state will simply be dp of m minus 1 n minus 1 equals 1, right? So that's our base state. Okay, so now how will we do the transition, or basically how can we find the value of some state given the value of other states, right? So let's say we are at some value, we are at some position I comma j, right? We are at some position I comma j, and we need to calculate the value of dp of I and dp of ij, right? So either we moved this way or we moved this way, right? So either we moved right or we moved down. So now if we moved right, we'd be stuck here, right? So not stuck here, we'd be at this position. And then again the problem would be the same problem, which would be the ways to count the paths down, the way to count the paths to the reach the end goal, and to the reach the end goal, right? Similarly, if we move down, again we would have the same problem. So basically what we can realize is we are simply summing up the way we can move right. So if we move right, that will be written as I comma j plus 1, and the way we move down, okay, so that will be written as I plus 1 j, right? So this is going to be our move right, move right, move down, move down. Obviously we can only move to valid states, so we need to keep track of that. This will be the current number of ways, current number of ways, right? So if we want to find the number of ways for the current position, it is simply the sum of number of ways for the right position and number of ways for the down position, right? So we can have this dp transition, we have this base state and goal state, and since each dp transition needs the value of j plus 1 I plus 1, all we need to do is we need to do dp from bottom to top, right? Bottom to top, right to left dp. Okay, so yeah, bottom up dp is pretty simple actually. Himanshu, I'm not getting what exactly your doubt is. If you have done the grid unique paths, it will be, yeah, like if you have done the number of paths in a grid dp problem, this will be very standard. I'm just explaining this to you, right? If you take the TLE course as well, this problem is discussed. So number of grid paths, I guess. If you have any doubts, just check out these articles. There's even, I think, USACO article on it, paths on grids. And they all pretty much do the same DP kind of idea. I hope you get it. So if you want a top down idea, you can see the top down idea here. I gave you the bottom up idea, which is the way I like to think about it. Okay. Yeah. No, this is not the full answer yet, V code. That's why we're not moving to the next question. There's still some part left to the answer. Okay. So now, once we have the transition down, why can't we simply do this transition? The reason is because we still have the mirrors, right? We still have to take care of the mirrors. So basically, what did we notice about the mirrors? Basically, if we entered a mirror from R, then we can only move down, right? Similarly, if we entered from down, we can only move right. So that means we cannot simply sum the number of ways from the right, number of ways from down for the mirror, but we need to follow the path which the mirror is taking us, right? So basically, let's say um, so let's put some mirrors over here. Okay, so let's say this is a mirror, some mirror, this is a mirror, and this is a mirror, this is a mirror, something like this. Okay, and the rest are zeros, let's say, which are not mirrors. Fine. Okay, so let's say we had some path which entered this mirror on the right, then it would be forced to go down. Then if it came down to another mirror, then it would be forced to go right. Again, it would be forced to go down, and then it could follow this path, right, to the end. So basically, our value is getting forced here, here, and here, right? So it is being forced. Okay, so I hope you get me. We cannot do anything but forcefully follow this path. Okay, so basically, if our right cell is a mirror, then we cannot follow it, right? We cannot just add dp of I. We cannot just add dp of ij plus 1, but we need to follow the path. We need to follow the dp path, basically, sorry, the mirror path, the path of the mirror, right? So what does that mean? What do I mean by following the mirror path? Basically, if I want to find dp of this point, okay, so this is dp of let's say this is dp of 1 comma 1, right? In the grid, this is 1 and this is 1, so this is dp of 1 comma 1. So dp of 1 comma 1 equals dp of 2 comma 1 plus dp of 1 comma 2, right? But for 1 comma 2 position, this is 1 comma 2 position, there is a mirror, right? And the mirror will force me to go like this, then like this, then like this, then like this. So I should follow this path, and I should add the dp value here instead. So what is the point here? This is 1 2 3, and this is 3. So I should add dp of 3 comma 3 instead. Okay, so instead of adding dp of 1 comma 2, I should add dp of 3 comma 3, because that is where my path of mirrors led me. Fine. So I hope you get this idea. Basically, we cannot simply directly add the dp value here, because that's a forced path. Once we reach the end of the forced path, then we can add the dp value from there, right? Because if we go right over here, that means that we'll reach forcefully over here, and then the number of ways from that position will be counted, right? So basically, for both right and down, if the next cell is a mirror, then follow the mirror path and add that dp value. Okay, so follow the mirror path and add that. And once the mirrors stop, right, and once the mirrors stop and you reach a normal cell, right, mirrors stop and you reach an empty cell, and you reach an empty cell, add the dp value over there, add the dp value of that cell. Okay, because that's the number of ways you are actually counting of that cell, right? And if you might think the time complexity of this is too much, right, The reason the time complexity is not too much is because nm is less than equal to 500. So that means we are going through the grid once, and then we are going to the length of the paths which we can follow, right? So it will be time complexity of big O of n times m times the maximum length of a path. Now the maximum length of a path will be at most n plus m, right? The maximum length of a path will be at most n plus m. So it will be basically n times m times n plus m, which is about big O of n cubed itself. Right, about big O of n cubed itself. So again, I repeat, while doing the DP updates, this is the standard DP updates. While doing this update, if I have a mirror on my right, I will follow that path and I will update this. If I have a mirror below me, I will follow the path below me. And then I will, whenever I reach a non-mirror cell, I will update the DP value at that cell, right? Because that is the number of ways which are actually getting counted, because the mirror paths will be forced paths. And the time complexity of it also fits within the constraints. So I hope this part is clear. Let me just show you the implementation of this. So we discussed the code, the logic and the time complexity. Now let's discuss the code. Obviously you need to have modulo, so we'll define a modulo. M and M is as defined in the question. We will create a DP vector which is of size m into n. We'll let it be zeros for now, right? Let it be zeros. And also our base case. So this is our base case, m minus 1, n minus 1 will be 1, right? So this is what we discussed. Now we will fill our DP values the same way we do grid DP questions. So if our last cell, if we are on a last cell, or we are on a mirror, we are not going to do it. Okay, so if we are don't need to calculate for mirror positions. Okay, don't need to calculate DP value for mirror positions. Okay, so that is one thing you need to keep in mind. We don't need to we don't need to calculate the DP value for mirror positions, because it's not needed, because if it's a mirror, we're just going to follow the path of that mirror, right? Okay, so now DP of ij is equal to right plus down percentage mod. What is right plus down? Right is the count of number of ways if we go right, and down is the number of ways if we go down, right? So this is right and this is down. Okay, but here we cannot simply write DP of ij plus 1 or DP of I plus 1j, because there may be mirrors over there, right? So what I'm going to do is I'll set right and down to 0. Then I will put my current I and current j as I and j plus 1. I'll put direction. Okay, so direction means the current direction we're moving. Direction can be right or left, right? So sorry, right or down, right? So for right I'll keep as 1, and for down I'll keep as 0, something like that. Okay, so while we are still in the boundaries, and we are still in the, basically we are still not, we are still in a mirror, then we will do I plus plus or j plus plus, and we'll switch the direction, right? So this means we are following the path of the mirror, right? Following the path of the mirror until we reach a non-mirror or a empty cell. That's what we're doing here, right? So we go right, and then we're following the paths. And then if the grid value is not equal to 1, that means that we have found the non-mirror, right? We have found an empty cell, empty cell. So we can simply set the DP value as current I and current j. Similarly, here my direction is going to be down direction, right? And again I'm following the path of the mirror until we reach empty cell, right? Or we go outside the boundaries, in which case we can just stop, right? And then once I find an empty cell, I add the DP of that. So for both right side and down side, I found the DP values, and I update my current DP with that. Finally, I return my base case, which is DP of 0, 0. Right? So it's a nice twist on the basic grid path problem. Yeah, for down also we have to follow mirror path. That's why this is for the right direction and this is for the down direction. Okay, so I hope everyone understood this. Any doubts, please put it on the chat right now. Any doubts, guys, or is it clear? Yeah. um, I'm not sure. There might be an n square optimization as well to solve the whole problem in n squared. But since the constraints allowed n cubed, this is the solution I thought of and I wrote. It's more intuitive as well, I think. Okay. Let's move on to the final problem, which is minimum operations to equalize a binary string. Okay. So this is a bit of a hard DP problem. You will again need to know DP as a prerequisite, and then you will need to apply your DP in a clever way to minimize the number of operations being used. Okay. And not only DP, like DP slash BFS problem. Okay. So let's get into it. What does the question say? The statement is pretty small. Let's just write it. Problem D. Okay. You are given a binary string S and an integer K. In one operation, you can choose exactly K different indices and flip each 0 to 1 and each 1 to 0. Okay. So you're given binary string S, integer K. All right. You can flip, you can choose K indices and flip each value, right? Basically, choose K indices and flip, right? Now we have to return the minimum number of operations to make the entire string equal to 1. If it's not possible, return -1. Okay, so that's what our goal is going to be. Yeah, question 3 was easier than question 2, I think. Right. So in this first observation, we can make pretty trivially. I'll just get into it right in a moment. So for example, 110 is our string and k equals 1. So we can just flip this bit and we get our number of operations performed is 1 to reach 111. Here they have given another example. The string is 0101. K equals 3 means we have to flip exactly 3 values at each turn. So they have given a way to do it, right? So they have said flip these positions and the string becomes 1000. Then flip these 3 positions and becomes 1111, right? So that's what we need to do. How could I solve all 4? To be honest, I solved only 3 in contest. This last one I solved 10 minutes later because I spent too much time on B and then I did not have time for this one. So in the contest itself, I solved only 3. Yeah. Although I had the idea, I was almost finishing implementing the 4th one as well, but I ran out of time. Anyways, and if you're asking in general, obviously if you practice more, you will be able to solve more questions. Trust the process, right? Okay, so let's simplify the problem. Instead of thinking of strings, right? First of all, the string itself does not matter. Why does it not matter? Because we can choose any k indices and flip them, right? So in essence, there is some number of zeros and some number of ones, and we are choosing some zeros and flipping them, and similarly we're choosing some ones and flipping them. So the actual positions of the zeros and one doesn't matter in the string, right? The actual position doesn't matter. It just matters that how many zeros are there and how many ones are there, because we can choose any k indices and flip them. So let me just show you. So let's write this observation. Observation 1. Exact string does not matter. Only the number of zeros. Only the number of zeros and ones are important. Okay, number of zeros and ones are important. Okay, so this is your first observation. And the second observation we can get from this is we can simply keep the state as so we can say our state is equal to number of zeros. Okay, so number of zeros can be our state. What does state mean? Basically that defines what current string we are at. Okay, because if we want number of ones is simply n minus number of zeros, right? Number of ones is simply n minus 1 number of zeros. So let's say number of zeros equals x. Number of zeros equal to x, then simply number of ones equals to k minus, sorry, n minus x, right? So I hope you got this part. So this is the only thing which is important, right? And our goal is to reach x equals 0, right? We need to reach x equals 0, and the operations we do will basically make, like if we choose one value from 0, let's say we choose one value from 0, we chose k minus 1 values from ones, right? From ones, and we flip them. That means that 1 0 will be less, but k minus 1 zeros will increase, right? Similarly this will happen for the number of ones. So we can basically track transitions in our state as well, right? So we can represent the problem. Let me just write that down. We can represent the problem as a dp, right? We can represent the problem as a dp where each state equals number of zeros in my current string. Okay, in my current string, right? So basically we have dp of 0, which means all of the there are no zeros in the string. Similarly dp of 1 means there's exactly 1 0 in the string, right? So the string can be something like, let's say 1111. This could be some string equal to something like this or something like this, right? Similarly dp of 2 will be some string equal to something like this or maybe something like this, right? This is for n equals 4. I'm giving you examples, right? So similarly there'll be dp of 3 and dp of 4, right? And they can correspond to different strings, but the strings themselves don't matter. It just matters the different states we have, which is equal to the number of zeros, right? And basically dp of I is equal to the number of operations required to reach number of zeros equals 0, right? Basically dp of 0 state using our flip operations, right? Using our flip operations. If we start with number of zeros equals I, if we start with number of zeros equal to I, okay, so I hope you understand what I mean by my dp states, right? So basically the only thing important about our current state is going to be the fact that the number of zeros which are there in the string. Okay, anyways, let's see. Can I have your username on Leetcode? My username is accordance. Once the like after the stream it will be edited and you will get the link to all the codes, right? You can see my username from there as well. Yes, you can do both. I agree with this advice, but also since you're in second year you have more time, so you can grind cp. I think that will be more helpful in the long term. Pradeep, cool, your idea seems interesting, but the way I did was a very generalized form. I didn't try to do greedy on this, because maybe there is some valid greedy, but I tried some basic greedies and they were not working out. So yeah, that didn't that's why I didn't do that. Anyways, so now let's think about how to do it, right? So okay, so now we're going to think about the transition. All right, so let's say my current number of zeros is equal to x. Okay, so what all can I flip it? So my number of ones will be equal to n minus x, right? So now let's say I flip k values, right? K values. In those values, I have z zeros, right? And k minus z are ones. Okay, so I have z zeros and k minus z are ones, right? So this is my current state, and this is the flip I'm performing. This is the transition I'm performing. So now what will be the new value of number of zeros? The new value of number of zeros will call x dash. Okay, so now the new state, this will be the new state after performing this operation. So the new number of zeros will be the old number of zeros x. Now the number of zero minus z. So I flipped z zero, so now they're ones. So minus z. But I also flipped k minus z ones. So those will be also removed. Those will be added. Sorry, those will be added. So basically my new state x dash is equal to x plus k minus 2z. Okay, x plus k minus 2z. So I hope this is clear how this formula came about. Basically, if my number of zeros is x and my number of ones will become n minus x. So if I flip k values and which are z are zeros and k minus z are ones, then my new state will be x dash equals x plus k minus 2z. Okay, because these zeros are getting removed and these ones have become zeros now. That's why. So let me show you an example just to clear this up. So let's say in my current state I have three zeros. And my n equals, let's say, 10. Okay, so my current state has three zeros and my n equals 10. So I will have like this, right? Some string like this. Then let's say I chose z equals 1. And my, let's say my k value was 5. Okay, my k value was 5. So if I take this z equals 1 and also take these four values over here, right? So total 5 values I flip these. So then my value becomes 0 0 1, and these ones become all zeros, and then the remaining ones are untouched, right? So basically what has happened is I have got a minus z. That means I chose 1 0, so that is getting subtracted from my number of zeros. But the ones I have chosen, which is k minus z, those will get added, right? So that's why the new number of zeros will be x plus k minus 2z. So is this much clear, right? This much should be clear. Okay, now the first thing, what is the maximum number of zeros I can pick? So maximum value of z, what is the maximum number of zeros I can pick? And that will be simply bounded by, it's going to be bounded by two values. One is x and one is k, right? So if there were many zeros in the array, then I can pick at most k zeros and flip them. Similarly, if there were not enough zeros in the array, then I can pick up at most the number of zeros in the array, right? So the maximum value of z which I can flip is equal to min of x and k. Okay, so there'll be some bounds over here, some math, so please follow it. Similarly, what is the minimum value of z? The minimum value of z will be equal to max of 0. So either I picked zeros to flip, right? I picked zeros to flip, in which case there's simply 0, but also it will be bounded by k minus the number of ones. Okay, because if there are not enough ones to be flipped, right, so then I can't flip zeros. I hope you understand. So let's say my array was something like 0 0 0 0 1 1. Okay, so in this case it is not possible for me. Let's say my let's give some values for k as well. So let's say k equals 4, right? K equals 4, n equals 1 2 3 4 5 6 7. So n equals 7, k equals 4. I cannot flip only wait, let me rewrite the test case. So yeah, so I cannot flip only zero zeros, because like I can't flip all ones, right? Because k equals 4, so I must choose at least two zeros. And the reason is because the number of ones is so less, the number of ones is so less, the number of ones which is equal to n minus x is so less, that's equal to 2, which is less than k, right? It's less than k. So that means that I must flip some number of zeros, right? So I must flip k minus number of one zeros, right? So that's where this comes from. Okay, so I hope you understand. If my current state is x, which is the number of zeros, and minus x is the number of ones, if I flip any k values out of which z are zeros, that means k minus z will be ones. The new state will be given by this formula: x dash equals x plus k minus 2z. The minimum value of z is this, and the maximum value of z is this, and the minimum value of z is this. Okay, and this is the logic behind it. So rewind if you missed it, but yeah, this will be important to us going on. Okay, so let's find out the minimum and maximum value of the new state, right? The minimum and maximum value of the new state. So new state x dash, what is the minimum value of the new state? It's going to be x plus k minus 2 min of x and k, right? So this is the minimum value of the new state, and the maximum value of the new state will be x plus k minus 2 times max of 0 k minus n minus x. So I hope you get this. And basically what the new state can question 2 and question 4 come in OA. I don't think these kinds of questions will be asked in OA, because in OA they ask more direct questions or more standard but hard questions, not these ad hoc type of questions. But yeah, they could come obviously, but the chance seems a bit less. Okay, so this is our new state. So let me explain what I mean by this. So simple intuition, okay, simple intuition. Let's say n equals 10, k equals 5. Our state is something like, let's say 0 0 0 1 1 1 1 1 1 1. Okay, this is our current state. So number of zeros is equal to 3. What are the possible flips I can do? One flip I can do is simply choose all ones, right? I can choose all ones. So I can choose z equals 0. I flip all these ones, and my x dash will be equal to 8. Okay, my x dash will be equal to 8 if I flip all these ones. So this is the first case, right? My x dash is equal to 8. Z equals 0, x dash equals 8, because I added 5 more over here, right? 3 plus 5 will be 8 zeros total. Okay, now what if I chose 4 of these and 1 of these, right? So now I chose basically 1 0 here, right? I chose 1 0, so that's going to be z equals 1, and basically my number of zeros will decrease by 1 and increase by 4, right? So the number of zeros are going to decrease by 1 and increase by 4, so they'll become 2 plus 4, which will be 6, right? So my x dash is 6. Similarly, for z equals 2, you can see that your x dash will be 4. Z equals 3, your x dash will be 2, right? So what if we flip these? Then this would become 1 1 1 0 0, right? I hope you understand. So basically we have these cases, either I flipped all of them as ones, or I flipped like this, or I flipped like this, or I flipped like this, right? In each of the cases we get these four cases, and that's what I meant by minimum value of z, maximum value of z, and minimum value of x, minimum value of x dash, and maximum value of x dash, right? So these are the possible transitions we got. Yes, Anshul explains your answer is perfectly right for problem 3. And yeah, that is a much more optimal solution than the one I told by being n squared. Anyways, back to problem 4. So these are the possible transitions from a given state, right? So we can have a solution like this. Okay, so let me give you a basic solution. We'll use a BFS. Okay, so BFS can start at 0 or BFS can start at the goal, doesn't matter. The BFS path length we just need to find, right? So we'll have dp of 0 equals 0, right? That is our target state. Then what we're going to do is we will do BFS. Every state which we can reach from 0, every state reached from 0 state, the path length will be 1, right? So the answer will be 1. Now simply every state reached from those states, the answer will be 2. Every state reached from those states will be 3. So say basically we'll do BFS and let x equal to the current number of zeros we are considering. So for each transition, if not visited this state, if not visited x dash, we can have dp of x dash equals dp of x plus 1. Okay, so I hope you get this part. This is going to be a basic solution, and in fact I had even written the code for this at one point, but then I realized that the time complexity of this would be too high. Okay, so let me just show you the code of this. Yeah, so this is a solution, basic dp solution. Wait, this part was later, right? Yeah, so basically if you find the size of the string and we create a dp vector of size n plus 1. -1 means it's unreachable or not visited, and dp of 0 is 0, right? Because that's our starting state. So the cost to reach the starting state from the start is 0. We'll push 0 to the queue. Each x equals the current number of zeros. Here t is the value of z. Okay, t is the value of z. So what I was calling z in my calculations, here I had called t. Okay, so basically the minimum number of zeros we can convert is this, the maximum number of zeros we can convert is this. So we find the value of y. If that value is unvisited, we can set dp of y equals dp of x plus 1, and we can push that value into the queue. We can push the value of y into the queue. In the end, we can find the count of zeros in the initial string, and we can return dp of count. Hello everyone. There was some issue. Is it fine now? Apparently there was some screen issue. Is it all right now? Yeah, okay. So like I was saying, the basic solution is the BFS solution. Basically, we can say that from each state, whichever states we can reach, we can go to those states and we can increase the path cost by one, right? And I already explained how to do the transition. So this was the basic code of that. Basically, we have a dp vector from 0 to n. Each value of dp means that the number of zeros in the string is 0, 1, 2, 3 up to n, right? So that's what the dp vector means. -1 means it's unreachable or it's unvisited so far. So we make a bfs queue, right? We make a bfs queue, bfs queue. For each value of 0, we push it from the, like, we take it from the front and we pop it. We see how many zeros we can convert, and for each transition, if dp of y was not visited, dp of y is equal to dp of x plus 1, and we push that to the queue and we finish our bfs. And finally at the end, we count the number of zeros in the string and we return dp of that count. Okay, so is this part understandable? Just go through this basic logic once. Any doubts, please ask it now, because we're going to optimize this after this. Okay, so is this clear, guys? Basically, we're doing a bfs. We're going to start at the 0 state and we'll do bfs to whichever states we can convert it to, and we will see what is the answer of dp of count, which is where count is the number of zeros in s, right? So the only state we are storing is the number of zeros in the string. Initially the number of zeros is 0 and the cost of that is 0, and then everything adjacent to that will get a cost of 1, and so on, right? So I hope this bfs is understandable. Even in the very start of the stream, I heard that people had done bfs, right? So I think you will be able to understand what this code is doing. Pretty sure a lot of people did this. Okay, so now the issue with this code is it's an n squared code, right? Our n was up to 10 to the power 5, right? So we cannot write n square code, and the reason is that time complexity of bfs, all of you should know, time complexity of bfs is equal to big O of n plus m, right? N is the number of nodes, m is the number of edges. Here number of nodes is fine. Number of nodes will simply be 10 to the power 5, right? That is the number of dp states. But m will not be fine, because the number of edges will be equal to, for each node we can have up to k edges, right? For each node we can have up to k edges, and k can be less than equal to n. So basically it will be big O of n plus n squared, which is big O of n squared, right? Which the time complexity is too high to do the bfs directly. So I hope that much is clear. So how do we improve upon the bfs? That is going to be the question. Okay, so now basically what we need to do is we need to find the answer. So dp of 0 will be 0, right? Now we need to find the answer for dp of 1, dp of 2, dp of 3, and let's say n was 6, so we need to find dp of 4, dp of 5, dp of 6, right? We need to find all these values, all these nodes, and like starting from dp of 0, there are some connections to some nodes. Similarly, dp of 1 is connected to some nodes, and if it was a general graph problem, this would be too hard to solve, right? But the thing is, the edges over here have a very clear pattern. The edges in this graph have a very clear pattern, and that is simple. That is because the number of zeros we are picking, the value of z, each time we have a value of z, it can go from z equals 0, z equals 1 to the maximum number of zeros in the string, right? So from zeros to maximum number of zeros in the string, we can pick that. The new value of the state x dash, that keeps decreasing by 2. Okay, so for example, x dash equals 8. Then if we take z equals 1, x dash will equal to 6. Then x dash will equal to 4. Then x dash will equal to 2, right? What is x dash? X dash is the new number of zeros after we perform the transition, right? So that is the new state. And the simple reason is the formula of X dash is this, right? X dash equals X plus K minus 2Z, right? Minus 2Z. So that means that each time is going to be consecutive even or odd numbers based on whether, if this is even, right? If this is even, then each time by subtracting 2 it will become the consecutive even numbers, otherwise it will be consecutive odd numbers, right? Because each time the next value is subtracting 2. Okay, so basically the minimum new state is this, the maximum new state is this, right? And we can subtract 2, we can add 2 or subtract based on what you think of. So we can add 2 and we add 2 again and we add 2 again until we reach this state. Okay, so that's what we are doing over here, right? So these are all the states which we can visit, and basically we can do a trick. Okay, we can do a trick. The number of states is fine, right? The number of states is fine. The number of states is simply 10 to the power 5, right? But the problem was number of edges was too much. Problem was number of edges was too much, right? Number of edges was too much, right? Which was equal to n times k. So what we can do is, for all the states which are not visited, we will store them in a set. Okay, so all the states which were not visited, we will store them in a set. Okay, they will be stored in a set. So as soon as we visit a state, we can pop it out from our set. Okay, so as soon as we visit a state, we can delete it from our set. As soon as we visit a state, we will delete it from the set. We will delete it from the set, so that it is never visited again. Okay, so that it will never be visited again. It will never be visited again, right? So basically that is removing the number of edges as well. We are only considering the nodes which are in the set, right? So for example, let's say our number of zeros was some 3. Let's say our x was equal to 3. This is the current number of n equals 10, k equals 5, right? So x dash, minimum x dash is 2, maximum x dash is 8, right? So basically the values of x dash can be 2, 4, 6, 8. We already showed this before, right? I had explained in this example why the values of x dash, which means the new value of 0, can be this. So basically starting from the state x equals 3, so from the state x equals 3, we can go to all these states, right? We can go to the state 2, we can go to the state 4, we can go to the state 3, 6, 8, so on, right? Similarly from these states we can go to other states, depends, right? So all these states are consecutive to each other, and we can have these states in a set. And basically what we can do is, let's say we have a set of active states, and we will find the minimum x dash value. The minimum x dash value we already have, right? We had already calculated the minimum value of x dash, which is this. The minimum value of x dash is this. So using binary search, we can find the minimum active state greater than this. Okay, so use binary search to find the minimum active DP state, to find the minimum active DP state. Okay, so this is a pretty advanced idea, so don't worry if you didn't come up with this, but yeah. And then similarly, in the set, and similarly use binary search to find the maximum one in the set. Okay, so use binary search to find maximum DP state in the set. Okay, maximum DP state in the set. Now what we have to do, we can do BFS, like add add all these states to the BFS queue, add all the states in between to the DFS queue, to the BFS queue, to the BFS queue, then delete the states. Okay, then delete the states. Okay, what is the state? State is simply number of zeros, right? So for each value of number of zeros, we will find from a current number of zeros which are the ones we can go to, which is the minimum, which is the max. We will take the active ones from the set using binary search. Everything in between the active one minimum, active one maximum, we'll do BFS on them, then delete them states. Okay, so because we deleted the states, we won't revisit them. So that is the main idea. And also one note we need to keep here, one note, we need to keep even and odd active states separately. Okay, even states, even number of zeros, basically even number of zeros, and odd number of zeros, odd number of zeros, they should have separate sets. Okay, so even number of zeros and odd number of zeros, they should have separate sets. And the reason is because each time we're doing +2 and -2, right? So even state, odd state, if they're mixed together, then again we'll keep visiting k states, k by 2 states each time. So that's going to defeat the purpose and not decrease our time complexity, right? So the states with even number of zeros and the states with odd number of zeros, they can form different sets. Let me just give you a quick example of what I mean. Okay, I'll give you a quick example of what I mean. So let's say we have n equals 0, sorry, n equals 10, k equals 5, and our initial x is equal to 0, right? So initial string is equal to 1111 11111. All right, our active states, active even states will be 2 4 6 8 10, and our active odd states, active odd state will be equal to 1 3 5 7 9. Okay, so these will be our active even, active odd, and we are doing an example right now to explain what my logic was. Okay, so this is an example. Now we start our BFS from our first node, which is x equal to 0. DP of 0 is already predefined to be 0, and we are doing BFS. First node is 0. Okay, first node is state equals to 0. That means number of zeros in the string is equal to 0. Okay, number of zeros equals to 0. Now from this, what is the transition we can do? We can simply choose a bunch of ones and convert it to zeros, right? So that's the only transition. So basically we can only go to DP of 5, right? DP of 5. So min x dash is equal to 5, max x dash is equal to 5. So what we're going to do is in the active odd set, right? Because min x dash is odd and max x dash is 5. So what we're going to do is add 5 to the BFS queue, add 5 to BFS queue, and then what we're going to do is delete it from active odd set, right? So now our BFS queue has 5 in it, and this value gets deleted from active odd. Okay, because we have already calculated the DP value here, right? Also DP of 5 will be equal to DP of 0 plus 1, right? So it will be equal to 1. Okay, so we have found the cost from reaching 5 zeros to 0 zeros is 1. All right, now the next node in our DFS will be, next node in BFS will be obviously state equals to 5, right? Now what are the zeros we can reach from here? Let's say we have 0 0 0 0 0 1 1 1 1 1, right? So obviously one way is to choose all of them and convert those to zeros. So that will be, total number of zeros will be 10, right? Otherwise we can have something like this. In this case the total number of zeros will be 8, right? And so on, and back to this we can have total number of zeros equal to 0, right? So we can have 0 2 4 6 8 10. All of these will be valid transitions which we can do. So basically the minimum number of x dash is 2, and sorry, minimum number of x dash is 0, right? Minimum number of x dash is 0. So 0 is already not in active even, right? So we won't visit that. Similarly, the maximum number is 10. Okay, so maximum number is 10. So the minimum is 0 and the maximum number is 10. So since 0 is already visited, we are doing binary search in the active array, right? So binary search for greater than equal to 0 will get us to 2, and less than equal to 10 will get us to 10, and all of these will get visited and then erased from the even array. Okay, all of these will get visited and erased from the even array. So basically we will visit all of them. So we'll say dp of 2 equals dp of 5 plus 1, right, which will equal to 2. Similarly, dp of 4 equals to 2, dp of 6 equals to 2, so on until dp of 10 equals to 2. And all of these will be removed from our active array, so they're never visited again. Now, each of these 2, 4, 6, 8, 10, those have been added to the queue, right? So one by one, we'll visit those. We'll visit like BFS will reach our node 2, right? And from node 2, which are the values which we can reach? So node 2 will simply be something like this, which will be 0, 0, 1, 1, 1, 1, 1, 1, 1, right? And now we will see how many zeros and ones we can convert. So if we choose this and convert it, that will make it 3 zeros. Then if we choose this and convert it, that will make it 5 zeros, and then this would make it 7 zeros, right? So 3, 5, 7. These are the next states, right? So again, in active odd, we'll go to 3, we'll go to 5, and we'll go to 7, and in between these we will update these dp values and remove them from the set, right? So that way we're visiting each node one time. So I hope you got this idea. I even gave you like a worked out example of how it goes. So here node 3 and node 5 will be visited. Sorry, node 3 and node 7 was visited. Node 5 was already visited, so nothing happens to that, right? So basically dp of 3 will be equal to 3, dp of 7 will be equal to 7, and those will be added to our BFS queue. They will be removed from the active states. Only 1 and 9 are remaining. So as soon as 1 and 9 are also done, then the whole BFS can stop. Okay, so that's the idea. Let me just summarize it. Summary. Basically it's our normal BFS plus DP, right? This BFS plus DP which we had, normal BFS plus DP, but optimize by keeping track of and removing active states once they are done, right? Active states. So this ensures that each state is visited at most once. This ensures that each state is visited at most once. We're taking advantage of the fact that they all are in like an increasing order, right? So that's why we can store them in set and we can all remove them at one shot, right? So is visited at most once. And make the complexity because we're using a set, right? So we're using so the time complexity becomes big of n log n, right? Let's have a quick look at the code. So the main change over here, a lot of the code is similar. The main change, let me just compare them. So see this part is pretty similar. The main change is this active set of evens and odds, right? So this is the active set for even and odd values of state, right? So this is the new thing added over here. We are going to check from the active set. Now similarly in the BFS, when earlier we were just doing all transitions and we were checking all of the transitions. Here instead of checking all the transitions, we're going to calculate first the start and end value. So that is simply this, using this formula on this and on this, right? So start and end value we get. Now based on the start and end value, if it's even or odd, we find lower bound for the start value, upper bound for the end value, right? So lower bound for the start value, upper bound for the up value. While the pointer to the start is not equal to pointer to the end, we will find the value of the pointer. We will update that value only. So we're only updating active values, right? So we're going to update this value like this, same way as before, and we will only update the active values. Then we will erase that from the set, right? So if it was odd, we'll erase it from the set of odds. If it was an even, we'll erase it from the set of evens. So this is an erase and pointer increment, right? Odds dot erase it start plus plus. So it's going to erase it and move the pointer front until it reaches to the end of the active set. Now once it is done, the rest of it is the same logic as the before DP. We just count how many zeros were there in the initial and return the DP count of that. Okay, so that's it. The optimization was mostly by keeping track of the active set, and the special trick over here was active set can be both, should be separate for evens and odds. So that's why we need to keep track of that here, right? So this active set type of DP has been seen before, like in AdCoder and stuff. I think I've seen before, to keep track of active states. But here the special trick or twist was that even and odd should have separate active sets, because otherwise that will defeat the purpose of time complexity, right? Because the states are like 2, 4, 8, and they have gaps. So that's why. So that's all for this question. I hope you understood it. I know it's a bit complicated, but yeah, it was the last question of the contest. Any doubts, you can ask it right now. You can also rewind the video and go through it carefully. Make sure you understood it, right? All right. So any doubts and any general doubts, I can take them now. Doubts. You can ask any doubts you have right now. Okay, Anand Chauhan, how to master DP and graphs in an efficient way? Well, first thing you need to do is learn basic theory, right? Learn basic theory either from TLE Eliminators or online resources, videos, online resource. And one particular nice one is Competitive Programmer Handbook, right? And also videos like people like Ericto and stuff. They have nice videos. So first learn basic theory, then solve problem sets, right? You should solve the classic problems, solve 30, 50 problems on the topic. Classic problems like there is AdCoder DP set, then there is CSCS DP set, DP and graphs both, graphs, right? CSCS website. You can go to CSCS. I think you will know CSCS. Just Google CSCS DP set or AdCoder DP set, you will get them. So that's how I practice. Most people practice. Once you have done like 30, 40, 50 questions, you will see most of the basic patterns and you'll get used to it. If you get stuck, do read the editorial, but don't read the editorial too fast. Otherwise, you will get used to it and you won't progress. Okay, also Unique asks, what is the best method of upsolving after attempting? I see the solution of all questions, but after editorials, right? So the thing is, I think my best way, my honest way is that first you should, like whichever question you got stuck at, you should take a pause, either the same day or next day, should come back to it and try it for 1-2 hours honestly, right? Genuinely by yourself. If you cannot, then you should read the editorial or see the video solution, and then you should try to implement it by yourself. So the implementation should always be by yourself. Don't just take someone else's implementation or just think, okay, I'm done. You should read the logic and implement it yourself. So that's my approach to upsolving. Also, yeah, if you revise them after a certain interval, that's great. That will help it keep fresh in your mind. And to be honest, I find your current way fine, right? You watch a video, you implement it yourself. That's a good idea. Okay, any other doubts? All right, then I don't see more doubts today. The Leetcode today was slightly harder, so don't worry about it. Again, a reminder to go check out TLE's Eliminators self-paced courses. They're in 4 different levels, and again, they have a lot of recorded lectures, practice problems, video solutions, as well as doubt support. So it's a very ordered, structured way to do your competitive programming, and it's for every levels, and it's pretty affordable in my opinion, right? So go check it out. Thanks for watching. Hope you learned something today. Do practice and upsolve the contest. See you next time, guys. Bye bye.